Hey everyone, and welcome. Today, we're going to tackle something that really throws a lot of people for a loop in differential equations: complex roots. What happens when your solution suddenly sprouts imaginary numbers? Well, let's dive in and find out. So picture this. You're working through a differential equation, it's all going fine, and then you get to the characteristic equation. You go to calculate the discriminant, that good old b squared minus 4ac, and bam, it's negative. So, what now? I mean, you can't take the square root of a negative number, right? Does that mean you messed up somewhere?
Nope, it's not a mistake at all. It's actually a signal. When your roots jump into the complex plane, it means your solution is about to start waving at you. Literally, sines and cosines are about to show up. This is the mathematical signature for any kind of oscillation.
All right, so let's break down exactly what's happening when these roots go complex.
See, when that discriminant is negative, the roots always show up as a team, what we call a complex conjugate pair. They have this exact form, a real part, which we call lambda, and an imaginary part, mu. So you get one root that's lambda plus I times mu, and another that's lambda minus I times mu. They're a package deal.
Now, if you plug these roots into our standard formula, you get this solution right here. And, mathematically, it's 100% correct. But for describing real-world things like a vibrating spring or an electrical circuit, it's kind of useless. How do you measure an imaginary distance? We need a way to translate this back into something we can actually observe. And for that, we turn to a true hero of mathematics, the brilliant Leonhard Euler, who gave us one of the most beautiful formulas you will ever see. Our source material actually calls this the magic identity, and honestly, it's the perfect name. This is the key that unlocks the whole puzzle and makes our complex solution genuinely useful. And here it is, Euler's formula. It says that e to the power of I theta is exactly the same as cosine of theta plus I times sine of theta. This is the bridge we were looking for. It's this absolutely stunning connection between exponential functions and trigonometry, and it's going to be our perfect translator. So when we take that messy, complex solution from before and apply Euler's formula, a little bit of algebraic magic happens, and everything simplifies down into this: a beautiful, clean, and, most importantly, an entirely real-valued solution. This is the formula you're going to want to remember. Think of this solution as having two parts working together. First, you've got the exponential part, the e to the lambda t. That part controls the overall amplitude. It creates an envelope that dictates whether the wave grows bigger or shrinks smaller over time. Then you have the oscillatory part, the sines and cosines. That's the actual wave, and mu controls how fast it wiggles, its frequency. Okay, enough theory. Let's get our hands dirty and see how this works in practice. We're going to solve a few occasions. First up, a classic case of what we call a growing oscillation. We need to solve the equation y double prime minus 4y prime plus 9y equals 0. The process here is pretty straightforward. First, you write the characteristic equation. Next, you use the quadratic formula to find the roots, and surprise, the discriminant is negative. From those roots, we can instantly pick out our lambda, which is 2, and our mu, which is the square root of 5. And finally, you just plug those numbers directly into our general solution formula. And that's it. You're done. All right, let's look at another one. This time, we're dealing with what's called pure oscillation. You'll also notice we have some initial conditions. That means we can go one step further and find the exact values for our constants, C1 and C2. So we start by finding the roots. And look at this. The real part, lambda, is 0. That's the signature of a pure oscillation. Why? Because e to the power of 0 is just 1. So that whole exponential part of the solution just vanishes. It simplifies things nicely. From there, we just use our initial conditions to solve for C1 and C2, and that gives us our final, very specific solution. Okay, for our last example, let's look at damped motion. This is what you see all the time in the real world, anytime friction or resistance causes oscillations to slowly fade away. It's the same process. We find the roots with the quadratic formula. And here's the key bit of information. Our lambda value is -1. This is the mathematical sign of damping. That negative lambda gives us an e to the minus t term, and that acts like a brake, forcing the entire oscillation to shrink and decay towards 0 as time goes on. We've done a lot of math, but what does this stuff actually look like? Let's build some intuition by visualizing these waves. Honestly, the entire behavior of the wave really just comes down to the sign of lambda.
It controls that exponential envelope we talked about. If lambda is positive, the envelope gets bigger and the oscillations grow, just like in example 1. If lambda is 0, the envelope is flat, and you get that constant, pure oscillation from example 2. And if lambda is negative, the envelope shrinks, damping the wave until it disappears, which is exactly what we saw in example 3. It's that simple. So, if you only take one thing away from this whole explainer, please let it be this. Getting complex roots isn't a mistake, it's not a dead end, it's a signpost. It's math's way of telling you, hey, the system you're looking at, it oscillates, it wiggles, it vibrates. This is the language of vibrating guitar strings, swinging pendulums, and alternating currents in circuits. So now that you have this incredible translator, the real question is, what other waves and vibrations out there in the world can you now describe with math?